Good morning.
Good morning.
Back in the spring, I gave you parts 1 and 2 of a little mini-series that I call Exploring the Solar System. And this, as you can see, is the third part, talking about how we use telescopes, either on Earth or close to Earth, to explore our solar system. So I'll be looking very briefly at 400 years of telescopes, looking at some of the very earliest views of our solar system carried out of order 400 years ago, and then considering some of the latest views we get of the planets in our solar system, and then asking what happens next. So Galileo didn't invent the telescope, but he was one of the first to actually point the telescope at the night sky and record what it was he was seeing. Since then, back in the early 1600s, telescopes have evolved and changed and, generally speaking, grown in size. There's always a desire amongst amateurs and amongst professionals to have larger and larger apertures, either lenses or mirrors. These days it tends to be mirrors because they're simply cheaper to make on a large scale. And the idea is if you have a larger aperture, a larger mirror, you can collect more light and you get more detail of the objects you're looking at. So you can see fainter objects, which usually means more distant objects, and you can see more detail in those objects. The largest telescope in the world when I was born was this one in the top right, the so-called Hale telescope with a 5-meter mirror. In other words, a 5-meter diameter at the bottom there. That's the size of the mirror. You can judge 5 meters. It's sort of more than half the size of this room or thereabouts. But of course, in the last few decades, not only have we had large telescopes on Earth, in the last few decades, we've been putting telescopes into space as well, such as the Hubble Space Telescope, launched in 1990. It's now 35 or more years old. It's an incredibly old telescope, but still producing wonderful work. And more recently, launched on, as it happens, Christmas Day 2021, is the James Webb Space Telescope. But that doesn't mean we're still not building large telescopes here on Earth. There are now projects to build ever larger mirrored telescopes, not simply something about 5 meters in diameter, which is one of the largest that was around decades ago. But now there are plans to build a telescope with a 40 meter diameter mirror, absolutely huge, made of segments, because it's very difficult to cast one mirror that's that large, so it's made in lots of smaller segments, and we'll come back to that a little later. But that's roughly what it looks like. I'm sure you can't really judge the scale, but that little tiny dot is a person standing in front of the telescope. So yes, 40-meter diameter mirror, absolutely huge, even compared to some of the larger telescopes that have been made in the last century or so. So let's go back to the start of the story. How did we explore the solar system back when the telescope was invented? Well, Galileo pointed his telescope in the sky. He saw a number of different interesting phenomena, including, for instance, when he pointed his telescope towards Jupiter, our own eyes show us 4 stars which wander around Jupiter, as does the moon around the Earth. A very important observation that he realized the little dots of light that he was seeing around Jupiter, he made a note of it in his notes, and he also recorded these dots going around Jupiter day after day or night after night after night, and concluded these dots of lights weren't just background stars, they are definitely little objects orbiting around Jupiter. This was the first proof that not everything orbits or revolves around the Earth. The Earth is not the center of the universe. Here we have proof because some objects are orbiting around Jupiter. When Galileo then turned his telescope on other objects, he, for instance, had a look at Saturn and got rather confused because he wasn't sure what he was looking at. At first sight, 3 round stars that in the middle considerably larger than the 2 lateral ones. So is Saturn 3 objects? Is it 2 humongous moons going around a central planet, or is it something else? Some people thought, well, maybe Saturn has got ears or handles or something. So the original view of Saturn was a little bit confused, and it didn't get much better for the next few decades. Part of the problem was that although the early telescope makers were developing instruments, it's not surprising that they weren't as well developed as later models. They didn't necessarily get or grind the glass lenses perfectly, and therefore some of the images that the astronomers were seeing through their telescopes were a little bit distorted. There was a little bit of aberration in the lenses, and so they weren't getting really sharp images. And that's why for decades, everybody who looked at Saturn was getting a slightly different impression of what they were actually looking at. Is it three bodies? Is it a body with ears? Is it a body with handles, etc.? A lot of confusion, and it wasn't until some decades later that one astronomer, Huygens, said, well, I think what we're looking at is a spherical body, much like other bodies we would expect, like the Earth or the Moon, but it seems to have a ring system around it. So a spherical body, a spherical globe with a flat ring system. And that, of course, is pretty much what we know is actually the case. Here's a much more recent image from the Hubble Space Telescope. So yes, back in the mid-1600s, it was realized that's what we're looking at. And it only appears to have different shapes if your telescope is imperfect. As telescopes got better, the imperfections were under control and people got a much sharper view of what's going on within our solar system. But you could argue that having imperfections in the optics was also responsible to some extent for the next part of the story, which is looking at the planet Mars. So Schiaparelli made notes here in his observation book of what are the features on Mars. And if you blow up on the right-hand side, you can see that he saw what he described at the time as canali. So channels. There seems to be straight lines on the surface of Mars. He called them channels. But unfortunately, channels got mistranslated from Italian into English as canals. And as soon as you call them canals, there is the implication that they are man-made. Correction, that they are not natural. So did Martians make these canals? So the original intention was just to say straight lines which are channels on the surface. And so maps were drawn up by Schiaparelli and others saying we can see features on Mars, we can see what appear to be ice caps, but the much more interesting is the fact that we have dark and light areas and lots of these lines everywhere. So in the 1880s, there were lots of maps drawn up by Schiaparelli and others, and many astronomers said, yeah, I can see those straight lines as well. And what are they? Well, some people picked them up as canals, and one in particular, Percival Lowell, in the 1890s and early 1900s in America, said, yes, I've seen these canals, and yes, it is obvious that these canals are unnatural. It is obvious that these were made by the Martians. And so in the late 1800s, we have the whole ethos of the War of the Worlds and the idea that Mars is occupied by Martians. They are building things on the surface of Mars, and maybe they are thinking of invading the Earth. So back in the 1800s and early 1900s, this sort of idea was rife. Percival Lowell in the New York Times here, Professor Percival Lowell, recognized as the greatest authority on the subject. Well, perhaps he believed he was the greatest authority on the subject, but he quoted here, there can be no doubt that living beings inhabit our neighboring world. So the idea of the existence of Martians, he was absolutely convinced that yes, Mars was inhabited. A lot of other astronomers were less convinced because they perhaps looked at Mars with their own telescopes and said, I'm not sure I can see these canals. Are they really there, or are they just a figment of our imagination? Percival Lowell used this rather large telescope in Flagstaff, Arizona. There's an image of him at the business end of the telescope there. And it is thought that what is actually happening is that people are being fooled into seeing certain features, not necessarily because the telescope optics are not perfect, but simply the limitations of the human eye when placed at the end of a large telescope such as this. A lot of light is being collected by the large lens at the front end of the telescope and being concentrated into a tiny eyepiece down the bottom there. What happens when you go to an optician and they shine a bright light in your eye? You tend to see the pattern of blood vessels on the back of your eye. Maybe the same sort of thing was happening. A large telescope and a small eyepiece was such that anybody looking at the surface of Mars might see fleeting glances of things that might look a little bit like straight lines, but perhaps they were looking at artifacts, possibly the blood vessels, or possibly they were just squinting down the eyepiece and believing they saw what they thought they saw, possibly because other people had suggested it. When one person says, I can see canals, when you look, are you going to say, no, I don't see that? Or are you going to say, yeah, I think I can see them as well? So it was a big problem. Schiaparelli drew lots of diagrams indicating straight lines joining various dark features on the surface of Mars. Others said, well, I'm not quite so convinced. I can definitely see some of the features you're talking about, but I'm not convinced these straight lines actually exist. Are you just sort of imagining the straight lines joining features, or are you looking at a few blobs and pretending or assuming that they are a linear feature? So the original view of Mars is covered with canals was eventually replaced with, well, no. As telescopes got better and ultimately photography took over, so we're not now subject to the rather subjective view of a person looking through a telescope. Now we can take images of planets. Well, we realize that there are no canali, there are no canals on Mars. There are definitely interesting features that are changing, but not canals. There are definitely ice caps, there are different regions. Some dark, some light. The idea that this might be vegetation has since been put aside. There's no vegetation on Mars as such. Amateurs, just like astronomers, are interested in buying telescopes and, where possible, the largest aperture. So you might start with a small telescope with a small aperture, but as your pockets get a little bit deeper, most amateurs would want to get larger telescopes with larger apertures to collect more light, to see fainter objects, to see more detail in the planets and, of course, the rest of the universe as well. Technically, any telescope that uses lenses are called dioptric. Any telescope that uses mirrors are called catoptric, but we tend not to use those labels, the scientific labels. We tend to call them refractors if they use lenses to refract light, and we tend to use simply reflectors if they use mirrors to collect the light. There are some designs of telescope which actually use a combination of lenses and mirrors, and because of the idea of dioptrics and catoptrics, they are known as catadioptric, but most people would simply call them cats. So there are reflectors, there are refractors, and there are telescopes that are a mixture of the two. And amateurs, as I say, if their pockets are deep enough, will try and get the largest telescope that they can. And some amateur telescopes are very large and very expensive. Some amateur astronomers take their hobby very seriously and would lust after a telescope like this, which is at the larger end and more expensive end of the market. And if you can't judge the scale, that tells you how big the telescope is. And yes, you'll need a small mortgage to be able to afford something like that. But the same is true of professionals. They will always want a larger telescope. And this particular graphic gives you an idea of the sizes of mirrors. So we're not worried about the size of the telescope per se. It's really just how big is the mirror that's collecting the light. And here to scale are mirrors of telescopes made over the last 100 or so years. So in the early 1900s, we have these tiny little dots here. The tiny little dot is a lens 1 meter in diameter. So it's an absolutely huge lens, but you can see it's dwarfed by the size of mirrors that have been made over the last century or so, through the 1900s and into this century. To give you an idea of scale, that one at the top there, not made of one solid piece of glass with metal on the surface to reflect the light. It's made of a series of smaller mirrors, a little honeycomb if you like, to make it easier. You can make each of these little segments, they might be 1 meter or 2 in diameter or across the flats of the hexagon. You put a lot of them together, you can make a mirror that's about 10 meters in diameter. Strictly speaking, we can't call it a diameter when it's a hexagonal arrangement, but you get the idea. The largest telescope in the world is that one at the moment, that one in yellow. It's the Gran Telescopio Canarias, and it's sitting on the Canary Islands. It's sitting on the island of La Palma. If we compare the size of that telescope with the size of telescopes that we've put into orbit, the space telescopes are in the bottom left-hand corner there. So the Hubble Space Telescope and the James Webb Space Telescope, there's the Hubble, that tiny little donut there in the bottom left, that little hexagon is the James Webb Space Telescope. There are other space telescopes which are smaller still. So you can see space telescope mirrors are nowhere near the size of the largest telescope on Earth, simply because although we would love to have a telescope that size, it's just too difficult to put into either Earth orbit or anywhere else. If we're going to have to put it on top of a rocket and then launch it into space, there are certain space constraints. In the case of the Hubble Space Telescope, it had to be small enough to go into the cargo hold of the space shuttle, for instance. In the case of the James Webb Space Telescope, it had a little bit of origami. It was folded up in order that you could put it on top of a rocket and then unfold it when you reach space. But you can see these mirrors that I've shown you, the largest in the world and the James Webb Space Telescope, for instance, they're dwarfed compared to some of the telescopes that are now being planned. And in particular, this one, astronomers are not good at naming things, so this absolutely humongous thing is called the Extremely Large Telescope, because they've already used the Very Large Telescope, and so now they had to find something bigger. They're running out of adjectives, so the Extremely Large Telescope, and this is the one with a diameter of about 39 meters. So you can see it's absolutely huge. And again, just to give you a sense of scale, just peeking into the bottom left there's a tennis court. And peeking into the bottom right, there's a basketball court. And you can hardly see it, but there's a human to scale. So these mirrors and the telescopes that they will go in are absolute monsters compared to even the large telescopes from last century, let alone the telescopes from previous centuries. So things are really moving as far as plans to build large telescopes on Earth, as well as the idea of having telescopes in space. So this is the one, in a sense, that I grew up with. The Hale telescope with its 5-meter mirror here. This was the largest telescope in the world when I was born. Remember, the largest telescope in the world now is about 10 meters, so it's only twice the size. So you could argue that's rather slow progress. If this was built, it was designed in the 1930s, built in the 1940s, and it was the largest telescope in the world for all of my childhood and a lot of my adult life as well. So the largest in the world is now only twice as big as that. But in a few years' time, we will have absolutely monster-sized telescopes. Where are these telescopes actually sited? Well, there are various places in the world where you'd want to put them. Ideally, somewhere where the atmosphere doesn't have too much of an effect. So the atmosphere doesn't necessarily absorb much light from stars or planets, but it does tend to be turbulent, and so it can degrade the image and you can lose some sharpness in the detail. So ideally, you want to get above as much atmosphere as possible. So you put them on mountaintops. So the best observatory sites in the world are, for instance, the Hawaiian Islands, volcanic islands, where you get weather systems that give you very clear, transparent viewing when you are 10, 12, 14,000 feet in the air or so. The same goes for La Palma and Tenerife, another set of volcanic islands, but obviously over towards Europe there. So a very good site. That's where the largest telescope in the world is at the moment. But the one that's being built with a 39-meter diameter mirror, that is going to be in Chile. In the high Andes, the Atacama Desert, very high, very dry, so you don't have much water vapor and you don't have that much atmosphere above you. A great place for putting telescopes. So yeah, you can put them elsewhere in the world, but those 3 sites are the best place to put them. If we have a closer look at what's going on in the Andes there, that gives you an idea of what it looks like. There's one observatory as photographed by another observatory on another mountaintop. You can see some haze and mist and cloud in the background, but bear in mind that the observatories are above that. Yes, there is cloud there, but the cloud is at a level below the observatory, so the observatory gets a nice clear view of the sky above. And if that's not good enough, if you simply want more of the atmosphere out of the way, well, you put your telescope in the back of a 747. So here, a 747 you can see operated by NASA, SOFIA, the Stratospheric Observatory for Infrared Astronomy. The idea is infrared light gets absorbed more than visible light, so you can't really do a particularly good job from ground level. So you take your telescope up in a 747, you fly it at 10,000 meters or more, and you get above an awful lot of the atmosphere. There's still some air above you, but not that much, and therefore you get some nice views. The infrared telescope in the back of the 747 has now been effectively replaced by the James Webb Space Telescope in space. Therefore, there's no need for this anymore. So that 747 is now being pensioned off. Just check out eBay every once in a while, because sooner or later that will be available. The same may be true of the Hubble Space Telescope, launched back in 1990. It's now 35 years old and going strong, but eventually it will fail. It's got gyroscopes to keep it pointing in the right direction. Eventually those gyroscopes are going to fail and it will be no longer any useful as a telescope. So again, perhaps in a few years' time, this will be retired. Again, watch out on eBay. You never know. The James Webb Space Telescope launched on Christmas Day 2021, so now about 4 years old. Took a few months to get into service, because once it was launched, it was built on the ground, fully equipped, but then had to be folded up. Basically, everything had to be folded up such that it fitted inside the shroud of a rocket, which could then be launched. So a little bit of very technical origami to get a large telescope folded up, including the mirror and the sun shield and everything else that keeps it nice and cool when it's out doing its job. It's not actually in Earth orbit. It's been sent 1 million miles away from Earth to get away from the heat of the Earth and the heat of the Moon, because it's an infrared telescope and you don't want any heat getting into your telescope other than what it is you're looking at. If we compare, what have we learned from the planets, for instance? If we compare the Hubble Space Telescope view with the James Webb Space Telescope view, the Hubble works essentially in the visible part of the spectrum and the James Webb works in the infrared part of the spectrum. So we get complementary information by looking with both of these telescopes at, for instance, what's going on with Jupiter. The composition of Jupiter, the colors that we see in the Hubble there, the oranges and the salmon pinks, etc., we think is a result of various elements, probably sulfur and phosphorus, getting churned up in the cloud belts. You see these very distinct cloud belts, which are very high winds going in different directions around Jupiter. Much like on Earth, we have trade winds going in different directions, and that produces storm systems. Well, on Jupiter, it looks the same. We have storm systems, the tiny dots here, as well as the big one here, the great red spot. That particular storm system appears to have been raging ever since we've been looking at Jupiter with telescopes. So that storm system has been going for 400 years. And we're trying to work out why. Storm systems on Earth generally build up and then dissipate. Why is this particular storm system one which has built up over we don't know what period of time, but doesn't seem to have dissipated much in hundreds of years? So we can hopefully get a better understanding of how atmospheres behave as well as how storm systems behave by looking at Jupiter. We get a different view if we go to the infrared. We're now looking at a different part of the cloud layer because we're looking at what's coming off in terms of heat from Jupiter rather than what's reflecting visible light. You might also notice a tinge of orange at the top and the bottom. That's not an aberration of the telescope, that's real. That's the aurora borealis and the aurora australis. So it gets aurora much like the Earth does. Charged particles from the sun are trapped by Jupiter's magnetic field, and those charged particles rain down onto the atmosphere and make the atmosphere glow with characteristic colors. When we have a look at Saturn, that's what Saturn looks like with the Hubble Space Telescope, a beautiful sight, rather better than the sort of sight you get if you had a ground-based telescope, especially an amateur telescope with a smaller aperture. You get a very nice view of Saturn, but not as distinct as this view from the Hubble Space Telescope. You can see at the back there the shadow of the planet itself being cast across the rings, and you can see some detail in the rings themselves. And the last talk I gave you about spacecraft showed how much more detail we can get if we were to actually fly a spacecraft to Saturn. But here we're talking about imagery using telescopes. If we were to look at Saturn with the James Webb Space Telescope and looking infrared, do we get a lot of different information? Well, it looks very different. You can see that we get very little light apparently coming from the body of the planet, and the rings look exceptionally bright by comparison. Why is this? Well, it's because essentially of the chemistry involved. The particular infrared wavelength used here is such that we're getting very little emission from the planet itself, In other words, we've chosen a wavelength in which the molecules of Saturn, the molecule in Saturn's atmosphere, will absorb infrared, so we don't get much light from the planet. But the ring system is a very large number of tiny icy particles which reflect infrared light very effectively. And so the rings glow very brightly in infrared light, but the infrared is absorbed by the planet itself. So we get this rather odd view of Saturn compared to the one we're used to with visible light. And the same is true if we look at other planets. This is the planet Uranus, which we have looked in more detail with spacecraft like Voyager that have flown past it. But here we see, again, the rings look much brighter than we're used to, simply because in infrared light, for the same reason as Saturn, the rings show up very brightly. In this particular case, Uranus seems to have a storm system. That's why there's a bright patch on the left-hand side. When Voyager visited Uranus, it flew past in a matter of hours. It might have taken years to get there, but it kept on going because it was on its way to Neptune. So it only passed the planet in a few hours. So it didn't have time to watch as maybe the planet developed storm systems. Now we have the luxury on Earth to actually have telescopes, either on Earth or in Earth orbit or close to Earth, that we can watch those planets essentially any time we like. We're not restricted to just the time period that we're flying a spacecraft past it. The same is true if we look at the planet Neptune. Again, Neptune looks fairly bright, and again, a ring system shows up quite brightly. What appears to be a very bright star, the star effect here is just a diffraction effect of the way light behaves when it reflects off a hexagonal mirror. This looks like a very bright star. In fact, it's not a very bright moon of Neptune. Neptune is quite bright. The moon isn't very bright, but again, in infrared light, the moon looks like it's even brighter than its planet. It's a bit like saying our moon is brighter than the Earth, which is the wrong way around. The Earth is very much brighter than the moon when you look at them from a distance. But here in infrared, because again, Neptune might be absorbing a few wavelengths of infrared, but Triton actually has a surface of nitrogen. It's solid nitrogen, which is very reflective in the infrared. And so that moon, despite being tiny compared to the planet, actually reflects a huge amount of light from the sun at infrared wavelengths. So what is next? Well, there are telescopes on the horizon that will be very interesting, and on the horizon means in the next few years. There's a big telescope that is essentially complete now. That shows it a little while ago while it was still being constructed. It was originally called the Large Synoptic Survey Telescope, which is a bit of a mouthful, and they've now decided to change its name. And they're now talking about this telescope carrying out a survey, legacy survey of space and time. That way you keep the acronym. So your domain name, lsst.org, you don't have to throw that away and get a new acronym for the internet. So this new legacy survey is use that telescope, 8-meter diameter mirror, and a huge camera. There's the camera with a person to scale. So this camera will be used with this telescope to survey the sky. So this isn't like the Hubble or the James Webb, which is told you've only got a small field of view, so go and look at that object and go and look at that object. This survey telescope is literally going to take pictures of the sky night after night after night and find out what is actually out there. In the process, it will almost certainly find lots of objects in our solar system. It'll also be finding galaxies and other things as well, but it will be finding asteroids, comets. It might even find a new planet. We think there are a certain number of planets, but maybe the planets beyond Neptune and Pluto, for instance. If there are, this particular survey will find them. So almost certainly the solar system is going to get bigger in terms of an inventory once this telescope has done its job. Notice the timeline. It's operational sort of now. It's up and running, but the survey hasn't started, and the survey will take 10 years, but in the first few months, it will probably find new asteroids and possibly a new planet if it's out there. And I've already mentioned this one, the European Extremely Large Telescope. The Americans are thinking of building a large telescope as well, but the Europeans have beaten them to it fantastic. It'll be operational fairly soon. It's in its final stages of construction, so 2028, another couple of years or so. Hopefully this telescope will be operational, and again, perhaps you can see a little more clearly a couple of people standing on the platform there next to some of the instrumentation, and a couple of people standing out the front. It is absolutely vast. It's going to collect a huge amount of light with its 39-meter diameter mirror, and hopefully it will see details that otherwise would be missing to us. So interesting times ahead in the next couple of years. So if I've piqued your interest, don't worry about making a note of any of these. They're on the handouts if you want them. The telescopes that already exist, the Hubble Space Telescope been around for decades, the Webb Space Telescope been around for a few years. There's all sorts of information on the relevant web pages, NASA and ESA, the European Space Agency, and telescopes that will be coming online fairly shortly, such as LSST and the Extremely Large Telescope. Again, the various agency web pages there will tell you more about why these telescopes were built, what they are doing, and what we hope to learn from them in the very near future. Thank you very much.